Great. Well, thank you for having me to the AFS Ontario annual meeting. This is my first one, so I'm excited to be here. The talks have all been great so far, and I'm looking forward to coming back to more meetings in the future. So the title of my presentation is an overview of the provincial fish culture and stocking program and of Normandale Fish Culture Station. So my name's Justin Chan, and I'm the Technical Development Coordinator for Fish Culture Section, which is in the Fish and Wildlife Services branch, which is part of the Ministry of Natural Resources and Forestry. So just a brief outline of what I'm going to be talking about today. I'll start with an overview of the fish culture and stocking program and give you some historical context, as well as the current provincial fish culture program and its management, and the role of fish culture section in fisheries management. Then I'll give you a virtual tour of Normandale Station, and then get into some developmental work and the external partners that fish culture works with. So from the mid-1800s into the 20th century, Ontario faced declining fish populations as a result of the combination of unsustainable harvests from commercial fishing, habitat destruction as urban centers began to expand and develop, the associated pollution from this rapid development, and demand for increased industrial capacity and the accidental introduction of exotic species from greater international trade. These factors led to a loss of fish populations, fishing opportunities, and genetic diversity in provincial waters. Some specific examples include the extirpation of Atlantic salmon in Lake Ontario, the loss and decline of lake trout and critical forage fish populations in several of the Great Lakes and inland water bodies, declines in lake trout and whitefish in Lake Simcoe, declines in lake trout and aurora trout in acid-stressed lakes in northern Ontario, declines in walleye in southern and central Ontario, as well as brook trout in inland waters. A federal hatchery and stocking program was established in the early 1900s. It was based on the assumption that because hatching rates could be dramatically improved under artificial conditions in hatcheries, stocking would thus enhance native populations. In 1927, the province became responsible for the fish culture program. However, stocking was relatively indiscriminate at the time, with little regard for the multitude of factors that affect successful stocking initiatives. The initial approach had the mentality of stocking lots of early life stage fish of many different species in as many places as possible. So hundreds of millions of fry were stocked from over 30 hatcheries. There was little consideration for genetic suitability, effects of stocking size, and ecological success factors like habitat suitability, carrying capacity, water chemistry, competition with other species, and disease risk. The general mentality at this time was a fish is a fish is a fish, and we should just put fish where we find other fish. Fortunately, to the next number of decades, culture and stocking techniques were refined and provincial infrastructure was consolidated. Modern fisheries management began in the 1970s with the development of the strategic plan for Ontario fisheries. This marked a shift to a more science-based approach to fisheries management, and the plan endorsed the use of numerous different tools, such as legislation and policy, fishing regulations, fisheries assessments and research, habitat enhancement and protection, invasive species and introduced species control, resource enforcement, and fish culture and fish stocking to guide management and sustainable development of Ontario fisheries. The most recent management plan was implemented in 2015 and is called Fish for the Future. The current Ontario fish culture program has two primary purposes. The first is to rehabilitate native populations of genetic. Yes.
Sorry to interrupt you. There's just a slight issue with your connection. I don't know if it's just me, but I don't know if you want to just turn the video off and just have your voice. Sorry to do that to you.
No, that's all right. Where I live, connection can be suspect, which is frustrating. So I'll turn myself off and hopefully that helps. Right, so the fish culture program has two primary purposes. The first is to rehabilitate native populations with the hope to reestablish self-sustaining populations. And the second purpose is to create, maintain, or enhance angling opportunities. This is accomplished through the stocking of native and non-native game species with the intention of establishing self-sustaining stocks. This is also supplemented by put, grow, take, and put and take stocking for in-demand and pressured game species with no specific intent of developing self-sustaining populations. To give an idea of the contribution that fisheries contributes beyond ecological management, just the recreational fishery value from Ontario angling was estimated to be $2.2 billion in 2014. And Craig, if there are any more connection issues, I can try switching to hotspotting my phone. So just let me know about that.
You're great right now. It's all good. Very clear.
All right, perfect. Thanks for letting me know. So a science-based approach is used to determine the state of Ontario's aquatic resources by implementing monitoring and assessment projects. These projects allow for research units to extrapolate ecological information from the environment to guide future management decisions. Stocking may be determined to be an appropriate management tool to help conserve biodiversity or to help enhance angling opportunities and alleviate pressure on sensitive stocks. It's really important to be completely clear that fish stocking is not the only management tool and that it is far from perfect. Fish stocking implemented by the provincial program is managed by planning units and authorities. The province is broken down into 20 fisheries management zones that are managed by districts and Great Lake management units through fisheries management plans. As it pertains to fish stocking, management plans guide the species, strain, life stage, and number of fish stocked into a water body, with additional consideration for the goals and objectives for that water body, its current and desired resource status, the lake capacity, angling pressure, and other stressors. Stocking requirements are then conveyed to us at Fish Culture Section through the annual production planning process, which is part of a 4-year planning cycle by the section's clients, who are the local districts and the lake management units. So there are currently 9 provincial fish culture stations located across the province that rear 12 different species of fish, consisting of 20 unique different strains. The map to the right shows the location of the 9 provincial stations, which are represented by the black fish, while the general coverage area that fish are stocked in the province is represented by the red overlay. Fish are produced from gametes provided by 18 captive broodstocks or that are collected from the wild from sexually mature fish and then transported back to a station. Some stations are more focused on broodstock development and maintenance and spawning, with most of their gametes eventually being shipped to other stations, while other stations are more production orientated, where these gametes are incubated and then the resulting fish are stocked. During the peak capacity period, up to 20 million eggs and fish can be in-house in the station at once, and annually almost 8.5 million fish with a total biomass of 200 metric tons are stocked in provincial water bodies. About half of these are stocked into the Great Lakes, with the other half going to inland waters, and 60% for population rehabilitation, with the remaining 40% to support angling demand. Approximately 2,000 water bodies are stocked each year that are part of a 4-year stocking cycle. A variety of different rearing systems are used in fish culture section in order to produce fish. These can be broken down into extensive and intensive systems. Extensive systems are a more traditional aquaculture system consisting of irrigated shallow outdoor ponds. Fish are reared at lower densities with lower rearing capacities compared to intensive systems. Due to the open nature of the ponds, they're subject to natural conditions and environmental inputs such as precipitation, natural photoperiod, temperature, wind, and local flora and fauna. This section primarily uses these extensive systems for the early rearing of walleye fry, in addition to some preliminary work with largemouth bass and bluegill. Intensive systems are a more modern system where fish are cultured at increased densities in units with higher rearing capacities. Many aspects of the rearing conditions can be controlled or manipulated to some degree, in addition to providing fish with a high nutrient and high energy formulated feed in order to maximize production and growth. The economy of scale in intensive systems is much greater compared to the extensive ones, and the majority of the section and the majority of the stations in this section produce fish in intensive systems. However, much greater technical oversight is required to effectively use intensive systems. Fish are stocked by Fish Culture Section at all life stages, from recently hatched fry to fingerlings to yearlings and up to retired broodstock throughout the entire year. Fish are initially loaded onto a truck or trailer at a station and are transported at a relatively high density so that each stocking trip has value compared to the amount of time in transport. The transport tanks are supplemented with oxygen and checked regularly to ensure that dissolved oxygen levels are at appropriate levels, and would initially inspect the signs for the fish for overt signs of stress. Depending on where fish are being stocked, they are initially driven by truck or trailer, and then they may be loaded onto ATVs or snowmobiles, flown by airplanes or helicopters, or transported by boat to their final stocking locations. This allows fish to be stocked into some very remote areas that would otherwise be inaccessible by road. Annually, fish culture drives around 170,000 kilometers, which is over 4 times the circumference of the Earth, in upwards of 400 trips, which equates to almost 150 days worth of stocking and driving. So now that you have a bit of a background on Provincial's fisheries management and the role that fish culture section plays within it, we can change gears to a more technical scope. Well, I'll give you a virtual tour of Normandale Fish Culture Station, where I can highlight some interesting technologies used, infrastructure and associated challenges, and a typical production of Atlantic salmon. So Normandale Fish Culture Station is located along the north shore of Lake Erie between Port Dover and Long Point in southwestern Ontario. Normandale Station was first built in 1925 and has undergone several renovations since then. Most recently, the station was rebuilt in 2012 after infrastructure began to fail, as prior to this rebuild, existing infrastructure was over 50 years old. Normandale was chosen to be rebuilt to address emerging fish culture program needs, such as supporting the Lake Ontario Atlantic Salmon Restoration Program, a new home for Chinook salmon production, and a central location to support the recovery of species at risk and of concern. Additionally, rebuild capacity and production capabilities, improve previous operational inefficiencies, improve broodstock rearing and holding, and address biosecurity and environmental concerns. The rearing facilities at Normandale prior to the rebuild in 2012 are pictured to the right, and were primarily outdoors in concrete circular tanks at both the main production station and at the substation. Since the rebuild, all rearing systems are now indoors and utilize modern intensive systems. Currently, Normandale produces 2 primary species for stocking into Lake Ontario, and they are Atlantic salmon and Chinook salmon. The substation is Normandale's broodstock facility and is geographically separate from the main station. It has its own power and water supply and houses mature lots of Atlantic salmon brood. The main station at the production facility, the main station is the production facility. All fish stocked by Normandale are grown from the egg stage, so the main station has infrastructure for egg incubation, early rearing, and advanced rearing. Normandale also has designated quarantine facilities, which can be CFI approved or Canadian Food Inspection Agency approved, to import and incubate eggs in aquatic species of unknown health or disease status. Effluent from these physically isolated rooms pass through a chlorination disinfection procedure to ensure that the downstream environment is not contaminated with any potential pathogens. Personnel entering and exiting from quarantine rooms are also subject to disinfection procedures and have to wear personal protective equipment to prevent in-station spread of disease. Some interesting residents that have included mud puppies, various darters and minnows, and a variety of mussels, Atlantic salmon from Vermont, and lake trout from New York have all been in our quarantine rooms. Normandale also has a small modular room that is used to develop expertise in rearing species of interest on a lab scale. I'll now walk you through some of Normandale's infrastructure, which supports the fish production inside at the main station. Water is supplied to the station by pumping surface water from a spring-fed creek running through the property, as well as by pumping groundwater from a series of 13 wells around the station. Both water sources require pumps to obtain the water and are thus reliant on a consistent power source to provide water to the station. Each fish culture station's ability to take water from the environment is regulated by the Ministry of Environment, Conservation and Parks by something called a permit to take water. And this is required for specific locations using a certain volume of water on a daily basis for certain applications. So this ensures that local aquifers and water tables are not impacted from these operations. Surface water passes through a drum filter to remove larger particulate matter before passing through a UV filter to destroy pathogens, while groundwater passes through a degassing column to remove dissolved gases and to increase oxygen content of the water. as groundwater is typically under-oxygenated. Both sources of water then mix in a large chamber in the aeration tower, pictured to the right, before being gravity fed into the station. After water passes through the station, the effluent containing excess feed and biological waste flows into a clarifier, where solid waste settles on the slope bottom and is scraped by a slow-moving bar to the deep end at the inflow. Periodically, the solid waste from the clarifier is pumped out and trucked away. Water flows from the outflow after a minimum passage time of 1 hour to the creek where it leaves the property as surface water. Effluent leaving the property must meet a variety of MECP requirements to make sure that waste and contaminant levels do not exceed certain levels, which could result in negative consequences for the downstream environment, with particular regards to total phosphorus and total suspended solids. Because Normandale is completely reliant on power to operate its pumps that supply water to the station, many of the systems are monitored by alarms and switches to notify us in the event of any failure or power issues, which would stop the supply of water to the aeration tower and to the hatchery. Hydro is supplied by 3-phase power by an above ground power line, but because the station is reliant on actively pumping water, this hydro is backed up by 2 emergency diesel generators. Some examples of monitored systems include power phase, where loss of hydro triggers an alarm and automatically starts one of the emergency generators so power can continue to be supplied. Water tower level to tell us if you're losing water from not pumping enough, or from pump failure, or from overuse, and flow switches. So we have to take every alarm call seriously, as the aeration tower can only hold enough water to supply the station for 10 minutes at maximum capacity without additional pumping. Picture to the right is our primary SCADA screen, which visualizes the main station's rearing units and all the monitored systems, the capacities that they are running at, and if there are any issues with the operation of anything being monitored. Normandale has a recirculating aquaculture system and is used for the end of incubation and the early rearing phase of Atlantic salmon. The recirculating system marks probably one of the pinnacles of modern aquaculture. Water reuse of 99% is attainable, and many aspects of water quality and the rearing environment can be controlled to maximize fish welfare and production. And there's a cost-effective temperature management to help control growth rate. Normandale's RAS consists of 3 independent systems of 17,000 liter rearing tanks per system. So picture to the right, you can see down the row of one of these systems of 16 tanks. Each RAS has its own filtration and mechanical system, which are housed in the adjacent room. RAS effluent initially passes through a drum filter to remove physical waste, then through a moving bed biofilter to convert nitrogenous waste into less harmful derivatives. Some water is then pumped up a degassing column to maintain a proper dissolved gas balance. All the water then passes through a UV filter to kill pathogens in the water before it is pumped up a small tower to gravity feed back into the rearing systems. A small amount of fresh water is continually added to make up for evaporative losses, and each tank has a freshwater valve, so individual tanks can be run on single pass fresh water if needed. Each RAS also has a heating unit, so temperature control is possible if it's required. Next, I'll walk you through a typical production cycle of spawn rearing Atlantic salmon at Normandale. Normandale substation, located 4 kilometers from the main production station, houses the Atlantic salmon broodstock that are used for producing the gametes for the Atlantic stocked into Lake Ontario. The demand for stocked Atlantic salmon comes from the Lake Ontario Atlantic Salmon Restoration Program, which is a multi-partner program and a provincial effort to reestablish a self-sustaining population of Atlantic salmon in Lake Ontario. Lake Ontario historically housed the world's largest landlocked population of Atlantic salmon before they were extirpated due to anthropogenic challenges and overfishing in the early 1900s. However, more recent lake conditions have presented as ideal for Atlantic salmon, and the Bring Back the Salmon initiative was implemented, with fish culture taking on the primary role in developing and housing Atlantic salmon broodstock and providing stocked fish for the program. Broodstock are housed in 20 15,000 liter raceways, which are part of a flow-through single pass system. To help conserve water usage, tanks are arranged in banks of 10 upper raceways and 10 lower raceways, with each upper raceway utilizing a top draining standpipe to divert 100% of the water to the lower raceway, which is then supplemented with fresh water. Feed is provided to each tank through a pneumatic system. The system has a built-in growth model, which allows it to automatically predict growth and provide feed to individual tanks according to growth trajectories based on feeding rate, water temperature, and energetic content of the feed. Technicians can manually update tank information such as average weight per fish and mortality so that the feed system can calibrate itself to accurately feed the actual biomass of the tank. In addition to feeding times, the percent of the daily ration per feeding, and various appetite factors. Feed is delivered to each tank through the black pipes in the picture on the right, which run overhead throughout the station to each individual tank before the feed is distributed through the length of the tank underneath the metal feed hood. We use a formulated extruded feed produced by EWAS, which is a West Coast Canadian aquafeed manufacturer that's a subsidiary of Cargill. Different feeds specific to life stage and to an extent species are used in the section. For example, nutritional demand for a gamete producing broodstock fish is a lot different than a juvenile fish. So different ingredients, additives, and macronutrient proportions are used depending on what is being fed. Lighting to the rearing area of the substation is provided by overhead incandescent lights wired to a sun-matched photoperiod controller. This allows the lighting system to mimic the day and night duration to what is naturally occurring outside at the substation's latitude. Photoperiod is an essential spawning cue for Atlantic salmon and must be managed correctly in indoor intensive environments to ensure that spawning occurs in the correct window. Atlantic salmon typically become sexually mature when they are 3 years old, and they are spawned according to a rotating line cross management plan. This allows us to preserve genetic diversity in stocked fish, which is important when attempting to reestablish a self-sustaining population. This also ensures that the creation of new brood lines do not become inbred. Maintaining wildness is of great importance in any rehabilitation effort. Care is taken to ensure that there is no genetic bottlenecking or selection of domestic traits. If done correctly, rotational line cross schemes can preserve adequate genetic diversity for up to 20 generations, assuming 3 distinct lines were initially used and can be kept separate into the future. Seen in the image on the right is the scheme that is used at Normandale to create new brood families. So 50 females and 50 males from different lines are crossed with each other to produce 50 new families for the next brood line. The line cross plans for the section are developed with a research scientist and a geneticist and are monitored and tracked through each brood lot's hatchery life. At Normandale, there are typically 4 brood lines in-house, 3 of which are mature and that are line crossed with each other as 4, 5, and 6-year-olds. Periodically, a wild collection takes place to reintroduce fresh genetic material into the broodstock. A number of fish from each lot are annually sacrificed and submitted to the Fish Health Lab at the University of Guelph to screen for disease and undergo pathogen testing, which helps to maintain the health status of this broodstock. The Sebago strain of Atlantic salmon at Normandale start to come online or have developed in free-flowing gametes towards the end of October through to early December. During this period, each tank of fish is sorted weekly to separate ripe females from males, which are called as their bellies physically feel hard, indicating that their eggs are still developing and not ready to be fertilized. Males are also taken as needed to a separate tank so milk can be collected. The next day, milk is collected by anesthetizing males and physically pressing on the ventral side of the fish to expel milk from the testes, which is collected in a plastic vial. Milk is then screened for viability under a compound microscope by placing a tiny amount on a slide and activating it with a drop of water. If milk does not react and remain static, it is assumed to be inactive and is not used for fertilization. Eggs are collected into a large bowl from females by anesthetizing them and physically stroking their ventral side in an anterior to posterior motion to expel their eggs. Eggs are then fertilized by adding milk to them, activating the milk by adding water and gently stirring the mixture. If a brood lining is being created, eggs are fertilized in a 1 female to 1 male ratio, while eggs for stocking and production may be fertilized in a 1 female to 2 male ratio if milk quality is adequate. Fertilized eggs are then disinfected internally before the micropile closes, then rinsed in water and then water hardened before being disinfected externally and then placed into incubation trays. Salmonid eggs are incubated in Keith stacks and upwelling trays, which mimic the riverbeds and the redds that salmonids would naturally create spawning beds in. Eggs cannot be handled 48 hours after layout, which is the developmental stage when an eye is distinctly and clearly visible in the egg. Not all eggs successfully fertilize or develop, and the dead ones turn opaque off-white color, while the ones that are still developing properly appear translucent orange in color with the aforementioned visible eye and notochord development. Normandale's Atlantic salmon incubation room has an egg capacity of over 1.5 million eggs, and with an eye-up rate of 60% sometimes, it is always guaranteed that there will be a lot of dead eggs to sort out from the live ones. Fortunately, there is a pretty neat piece of technology called an egg picker, which can automatically sort eggs for us rather than having to pick out hundreds of thousands dead eggs totally by hand. So eyed eggs are loaded into a hopper of the egg picker and are fed onto a vertical disc with a row of holes along the outer edge that individual eggs can sit in. The edge of the disc rotates across a light sensor, which can detect if light can pass through an egg or not, which indicates whether or not it is still alive. The sensor communicates with two air compressors, which ejects eggs with a light puff of air into a good or bad container. The good eggs are returned to a Heath tray where they can continue to develop and incubate, while the dead eggs are thrown out. Towards the end of development, eyed eggs are moved in Normandale's recirculating aquaculture system. The eggs are placed in a hatching basket, which rests above a plastic substrate, which sits in a trough. As you can see in the picture to the right, the trough is placed between two circular tanks to utilize the plumbing for incoming and outgoing water. As the eggs hatch, the sac fry fall through this basket into the substrate. They continue to grow with energy and nutrients provided by their yolk sac. Through this process, technicians use a set of picks or tweezers to continually remove dead eggs and fry. Without constant attention to removing mortalities, fungus and disease can propagate extremely quickly through a trough, which negatively impacts the surviving eggs and fry and can perpetuate greater mortality. As sac fry develop, the plastic substrate is removed. Prior to the start of exogenous feeding, the fry are removed from the trough and dropped into a low depth, low flow, early rearing circular tank, where a formulated dry feed starts to be offered to them. Fry are encouraged to swim up to the water surface by hand feeding multiple times per day, but a frequent cause of early mortality is fry's inability to begin exogenous feeding. As fry get on to feed and develop in size and swimming ability, water depth and flow rate can be increased as fry transition into the early rearing phase. The early rearing typically is in the early new year when all fish have been dropped down and have begun exogenous feeding. As mentioned previously, early rearing occurs in the recirculating system, which allows for control of almost all environmental variables. Normandale uses an extended photo period, temperature control, and a feeding regime that accelerates growth beyond typical cooler rearing temperatures and shorter daylight hours. Mortality is low with few disease issues. However, if there is ever any concern, samples are submitted to the fish health lab for analysis. And occasionally prophylactic peroxide or salt baths can be used to help improve fish health. The station also does have a veterinary use permit for halibut or chloramine tea if required, though this is typically very rare. Each individual RAS tank has a dissolved oxygen probe, which can be monitored remotely, in addition to an oxygen infuser that can automatically deployed based on the probe's readings. Each tank also has a valve that can direct effluent out of the station to the clarifier rather than back to the RAS filter, and a separate header line to deliver fresh water if needed by a turn valve. An overhead feed system delivers feed pneumatically and is run on the same program that is used at the substation. Normandale stocks Atlantic salmon at 2 life stages out of the early rearing RAS, as fry around 6 grams and as full fingerlings around 40 grams. As fry are stocked out, remaining fish can be redistributed into the empty tanks to reduce rearing biomass and encourage greater growth for stocking at later life stages. Approximately 300,000 fry and 70,000 fall fingerlings are stocked out each year, with 100,000 fish progressing to the advanced rearing stage to be stocked out as spring yearlings the following year. Advanced rearing occurs in identical rearing system as the brood stock in substation, consisting of 10 upper raceways and 10 lower raceways, utilizing a single pass flow through system, and the same automatic feed system and photoperiod controller. AR is also equipped with an emergency oxygen system that automatically deploys from a bulk pack from a solenoid in the event of power loss, which would otherwise stop water pumping capabilities and the delivery of oxygenated water to advanced rearing. Atlantic salmon enter advanced rearing in the summer when more space is required by the fall fingerlings in the early rearing recirculating system to reduce their density, and are grown until they are stocked as spring yearling smolts the following April. Fish are fed a commercial salmon diet produced by EWAS in a variety of sizes based on the average size of the fish in each tank. Advanced rearing is a flow-through system and does not have any temperature control, so growth rate is slower than in RAS, though fish are typically between 16 to 80 grams at their time of stocking in April. In addition to Atlantic salmon, Normandale has a regular production of Chinook salmon. Chinook salmon are originally from the Pacific coast, but were introduced to Lake Ontario in the 1960s as a means to control the invasive alewife population. Chinook were well suited for life in Lake Ontario and successfully established themselves as a proficient piscivore, as well as a popular sport fish, and their angling demand for them since the 1970s. Chinook are terminal spawners and naturally die after they reach sexual maturity and give up their gametes, which occurs after 3 or 4 years. As such, it's pointless to have a broodstock of Chinook salmon if you raise them for 4 years and then they spawn once and then you lose them because they naturally die. Chinook also struggle to naturally reproduce in Lake Ontario due to the high amounts of thiaminase in their prey fish, primarily from alewife and rainbow smelt. And this results in a thiamine deficiency causing early mortality syndrome in the next generation, resulting in extremely poor juvenile survival. So fish culture assists in stocking Chinook salmon to keep their population prevalent in Lake Ontario. In order to collect gametes for intensive production, Normandale works with volunteers in the Lake Ontario Management Unit to collect gametes from wild Chinook that run up the Credit River. Mature fish are caught using a crew with large dip nets and electroshocker that stuns fish, allowing them to be caught more easily. As you can see from the little video, it's not actually that easy because only the fish right around the shocker are stunned. The rest will run in any direction. And the fish are fairly large, so it's like a 20-pound torpedo coming at you. After the fish are collected, they are sorted into pens based on sex, so male and females, before their gametes are collected. Gametes are captured at the collection site and are transported back to the station, where eggs are then fertilized with milk. Eggs are collected by air spawning, where a female's body cavity is filled with air to expel eggs. Incubation and husbandry is similar to Atlantic salmon, except fry are reared in slightly different early rearing units, which are flow-through tanks, and they are not reared to older life stages. Fry are stocked directly into tributaries or into net pens in Lake Ontario. When in the net pens, they continue to grow and develop with community assistance until they are released from the pens after at least 3 weeks. The purpose of keeping them in the net pens is to allow them to imprint on adjacent river mouths to return for the spawning run to a new environment, minimizing predation, and learning to feed on live prey safely. Fish grown at Normandale are all stocked in Lake Ontario or its tributaries in the spring and fall, with stocking sites represented by the green dots on the map on the right. When it comes time for stocking, fish are loaded into a truck or trailer, either by manually lifting nets and buckets, netting fish into a large tote full of water with a bottom valve that can be driven and lifted by a forklift to the stocking truck, or by using a fish pump in a dewatering tower. The fish pump is kind of a cool piece of tech that operates like a large wet vacuum, and it just sucks up water and fish and pumps them in a hose to different locations. So we use the fish pump to move fish from early rearing to advanced rearing, as well as to load trucks with fish. When loading trucks for sorting, the fish and water are pumped up to an elevated water which allows the water to drain off, leaving only the fish, which are then diverted by gravity to the truck. The dewatering step is necessary as the fish pump can move up to 3,000 liters of water in a minute, which would otherwise overflow the transportation tanks in a few seconds. Fish are typically transported at relatively high densities compared to what they are reared at, often over 100 grams per liter, which is considerably higher than as I said in their regular rearing units. Oxygen is diffused into the transportation tank from K bottles to ensure that dissolved oxygen content is sufficient for the fish, and readings are taken frequently during each stocking trip. Some additional past, present, and future husbandry that Normandale has been or will be involved with includes work on freshwater mussels, a deep water core-gonid species called bloater, and bluegill and largemouth bass. From 2014 to 2018, Normandale worked in conjunction with the DFO in developing expertise in rearing native at-risk mussel species. These included the snuffbox mussel, the northern riffle shell mussel, and the wavy rayed lamp mussel. Gravid females were collected from the wild and taken back to Normandale, where host fish were infested with the female mussel's parasitic glaucidia. The glaucidia develops on the fish's gills, and then they drop off the fish and were collected and reared in a variety of different systems to later life stages. Fish culture section developed successful techniques to rear mussels, but unfortunately the program was terminated in 2018 when the responsibilities of species at risk was transferred from the MNRF to the Ministry of Environment, Conservation and Parks. Bloater or deep water core-gonid whitefish species that was extirpated from Lake Ontario in the 1950s. Bloater actually got their name because as fishermen caught them and brought them up from depth, because they lived so deep, the change in pressure actually caused them to bloat outwards, and they got their common name bloater from that unfortunate characteristic. There's a binational program to reintroduce bloater to Lake Ontario and assess the feasibility of restoring the historic deep water prey fish community. And that's especially relevant now with the interest in bringing back predatory fish like Atlantic salmon and lake trout to Lake Ontario. Fish culture section developed the first in-house bloater broodstock and cultures bloater at Normandale and 3 other stations to contribute to this reintroduction initiative. Coming up this summer, largemouth bass will be cultured at Normandale to help support the emerging demand of urban fisheries around the Greater Toronto area. Gametes will be provided from a captive broodstock and reared in an intensive system, which is different from the majority of bass culture, which normally utilizes extensive pond systems for typical production. So we'll have a learning experience this summer, and hopefully we can So I'll now talk about some research collaborations and developmental work that fish culture section does. So the section works with numerous external and internal partners to improve aspects of the provincial fish culture and stocking program. These include research scientists in other parts of the government, like the Aquatic Research and Monitoring Section, lake management units and the DFO, professors and academics at universities and colleges, industry experts, and international partners. There are several broad objectives when pursuing developmental work for us, and these include improving husbandry practices for species currently reared in the fish culture system, developing husbandry practices for species that have not been previously reared, exploring strategies to improve or enhance post-stocking survival of cultured fish, and supporting research on assessing and monitoring stocking initiatives. Listed here are some of the groups that Fish Culture Section has collaborated with to further research interests related to fish husbandry, stocking, survival, and recovery. I won't just read everything off the screen, but some projects of particular interest include genetic tracking and broodstock integrity by Chris Wilson, gamete physiology and fertilization and incubation success by Trevor Pitcher, investigation of nutritional adequacy of aquafeeds and improving feed formulations by Dominique Bureau, and acoustic telemetry and assessment of post-stocking performance by Aaron Fisk and Tim Johnson. A few concrete examples of recent developmental work that fish culture has done to improve species knowledge and operations are shown here. The intensive culture of walleye has been something that we have been working to improve at, as walleye culture occurs mostly in extensive ponds in the early life stages. Walleye are extremely cannibalistic species, which presents some unique rearing challenges in intensive environments. But the economy of scale and producing magnitudes more walleye in smaller spaces, and the fact that groups in the US have had success with walleye in intensive systems are strong motivators for this work, in addition to a high demand for stocked walleye. In the bottom picture is a picture of one walleye eating another walleye of essentially the same size. So they will literally try to eat anything that they can get their mouth around, and they can open their mouth pretty big. Enrichment of Atlantic salmon to improve post-stocking survival is a major project that Normandale is currently working on now, and I'll speak about this in greater depth shortly. As mentioned earlier, bluegill and bass are a new culture initiative to support a demand for a put-and-take urban fishery in the GTA. So these species are completely novel to the section, so there'll be a lot to learn in the upcoming season. Our protocols were developed from consultations with similar departments and agencies to fish culture section and the MNRF from different states that grow bass for their own stocking programs south of the border. One more project of interest pertains to effluent management and wastewater exiting fish culture stations. We are working with Fleming College and Gord Bulk to develop strategies to manage total phosphorus levels in our effluent and in the water before it leaves the station property, as per MECP limits. Possibilities include constructed wetlands to increase effluent residence time and phosphorus uptake, and feeding strategies and formulations to minimize phosphorus waste. The last piece of developmental work that I want to talk about is an environment enrichment project that is currently underway at Normandale. The background of the project stems from concern that stockfish are not well prepared for introduction into the wild environment, and they may struggle with sourcing prey, avoiding predators, and adapting to novel conditions not experienced in hatchery. This work is based off of a master's project by Justine McAndrews in 2019 at the University of Windsor, who was supervised by Professor Aaron Fisk. Environment enrichment consisted of in-tank structures in the early rearing recirculating system and exposure to larger predators, a variety of different scents, and live food. The fish that were enriched were implanted with passive integrated transponder or PIT tags, or acoustic telemetry tags, which allowed them to be tracked as they passed different array networks. Justine achieved positive preliminary results, which encouraged us to pursue enrichment further. We built on Justine's work and adapted it to part of Normandale's advanced rearing facilities in 2020 to enrich Atlantic salmon yearling smolts with 4 primary elements. Water velocity was greatly increased by converting raceways into burrow-style tanks. So pretty much turning a rectangular raceway tank into an oval by placing a divider in part of the tank and utilizing 2 airlifts to generate a circular current. Enriched fish also had periodic exposure to live predators and were occasionally fed live prey to simulate more wild conditions. Prey items included black soldier-fly larvae, salmonid eggs, and lake choke fry. Enriched fish also had in-tank structures to break up the monotony in the shape and color of a normal raceway. To assess how the enriched fish performed compared to typical production fish, we tested scent association, new predators, and danger in a small aquarium system using a peristaltic pump and video cameras to record behavior, and utilized a swim flume, which is essentially a water treadmill for fish to test their maximal swimming speeds and swimming performance. Finally, post-stocking survival and downstream migration to Lake Ontario was tracked using pit tags and 2 arrays in the tributary that the smolts were stocked into. Enriched and normal production fish were stocked at different paired sites, and we observed that a far greater number of enriched fish successfully migrated downstream, as shown on the graph to the right. Based on these tentatively promising results, we have scaled up our enrichment efforts this year and improved on a number of procedures and are planning to stock a greater number of pit tagged fish to generate stronger results from pit tag arrays this year. We received a lot of good advice, and I'd like to thank our advisors for their efforts in improving the Atlantic salmon stocking program, including professors Colin Brown, Grant Brown, Aaron Fisk, and Trevor Pitcher, as well as Dr. Chris Wilson. Going forwards, fish culture section aims to continue to meet the current stocking demands in Ontario as set by the various districts, FMZs, and lake management units. And we want to continue to improve our rearing practices, husbandry skills to advance stocking capabilities, production capacities, fish welfare and efficiencies, while developing expertise with new species to meet future demands. We also continue to collaborate and communicate with various partners and groups to advance fish culture in the section and beyond. So thank you for hanging around on a Saturday afternoon to listen to my presentation. Hopefully you learned a little bit about the fish culture section program as well as the stocking program. I'm open to any questions that you may have now. If there's anything I can't answer, feel free just to email me and I will try to get back to you with an answer.